Hello, in today's video, we are going to be working with K, the equilibrium expression again, and we are going to see how K changes if we reverse the reaction, if we double the coefficients, and so on. And then in our next video, we will get into calculating K given some of the concentrations. So first off, in the previous video, our last slide talked about the value of K and what that told us about the direction of the equilibrium. So if the forward or the reverse reaction was favored. So we're just going to review that real quick. All right, so as a review, if our value of K is large, so much greater than 1, then that tells us that the products are favored or the forward reaction is favored. If K is small, now K can never be negative, but it can certainly be less than 1 and have a negative exponent, then our reactants would be favored and the reverse reaction would be favored. So just wanted to start by reviewing that. We know that one direction, forward or reverse, will always be favored and will be thermodynamically favorable, and the other one will not be. So if K is large in one direction, say for the forward reaction, then for the reverse reaction, it would be very small. When we try to reverse the reaction, we will need to take the reciprocal of K. So we do not negate it because K can't be negative, but we will reverse the products and the reactants. So remember, K is concentration of the products over the concentration or pressure of the reactant. So if we're reversing the reaction, we reverse that. So we'll take the reciprocal of that. So if this is our reaction here, and K for concentration has a value of 2.12. If we reverse the reaction, then it would just be the reciprocal of that. So 1 divided by 2.12, and put that into your calculator. And that gives us a value of 0.472. So again, if you are reversing the reaction, you're reversing your numerator and denominator. So hopefully it makes sense that you are taking the reciprocal. And hopefully it also makes sense that it'll be big in one direction, smaller in the other direction. All right, if we change the stoichiometry of the reaction, that will change the value of K. So if we are, say, doubling the reaction, what we will do is we will just raise everything to the power of 2. Because remember, our K is products over reactants, but we do take the stoichiometry into account. So, and the stoichiometry is going to be our powers. So if we are changing the stoichiometry, we have to change the powers. So if we take a look at our first example here, we have this reaction and the K value is 4.6 times 10 to the 4th. So what we are doing with our second example is we are tripling the reaction. We are not reversing it. So K will still stay large. The forward reaction will be favored, but we are changing the coefficients. So my new K is going to be equal to the old one, 4.64 times 10 to the 4th, to the 3rd power, because you'd be changing all of the coefficients. So you'd be changing all of the powers in the K expression. So you just change the power. So then we put that into our calculator, and that gives us 9.7 times 10 to the 13th as our new value. All right, so now we just have some examples here. So we want to write the equilibrium expression and then figure out the value too. So if this is the reaction they gave us, and then they want it for the reverse. So the reverse would be 2Br, gas goes to Br2. So my new K would be Br2 over the concentration of Br squared. We don't have the concentrations, but we do have K. And since I flipped the reaction, I'm doing the reverse of it. I would take the reciprocal. So it would be 1 over 2.2 times 10 to the negative 15th. And that would give me a value of 4.5 times 10 to the 14th would be the new value of K, which makes sense because going in this direction, we had a very low value telling us it was not thermodynamically favorable. So therefore, if we reverse the reaction, then it would be thermodynamically favorable, and you would have a K much greater than 1. All right, so this next example is just a continuation of our previous one. So they give us that original reaction, except it's been cut in half, but they want the reverse of that reaction. So we would want Br to 1/2 Br2. And we are looking for the value of K. So that is basically the reaction that we just did, where we got K being 4.5 times 10 to the 14th. However, the coefficients have been changed. It is 1/2 of what we did before. So we would take that K from the previous one, and that was 4.5 times 10 to the 14th. And we would put that to the 1/2 power, which is the same as the square root. So then we just put that into our calculator, and that would give us, all right, that gives me 2.1 times 10 to the 7th. Now your value might differ slightly. I did what was already in the calculator from before, so the decimal here could vary a little. So to review, we took that original value, we took the reciprocal of it when we wanted the reverse, and then we also changed the coefficients. We cut them in half, so therefore we took it to the 1/2 power or square root. All right, another thing that we can do with our K values is we can combine multiple reactions to one net overall reaction and get an overall K. So it's kind of like Hess's law back when we were doing thermodynamics and we had a delta H of, say, 3 different reactions, and we summed them up, and maybe we had to flip flop, reverse them or double them, and then we made some changes to delta H, got the overall delta H. So it's the same type of thing. We are given 2 reactions here, and they give us their K values. And then we are looking at our net reaction, and we're looking at the K. We're trying to find the K for the net reaction. Now, this example is fairly straightforward because we don't have to double or reverse any of the reactions we've already been given. So if we just add up these 2 reactions, we would see the silver ion would cancel, and we would end up with the AgCl plus the 2NH3, which is what we have, produces the AgNH3 ion and the Cl ion. So we didn't have to double anything. We didn't have to reverse anything. Therefore, we can just combine the 2 K values that we already have. Now, think about with our new one, what we are going to be doing is we are going to be taking products over reactants. So it would be the concentration of the AgNH3 ion times the concentration of the chloride ion divided by the concentration of the NH3 squared. The AgCl would be left out because that is a solid. If you look at these 2 examples, you're basically just multiplying them, and not basically, you are just multiplying them. The AJ's again would cancel out. So what we do is we just do K1 times K2. So we just take the 1.8 times 10 to the negative 10th and multiply by 1.6 times 10 to the 7th. And that gives us a value, once we plug that into our calculator, of 2.9 times 10 to the negative third. All right, so I'm going to go through again how we got that and why we got that. So when we are combining our equations, you want to multiply the two K values together, because you would be taking all of the products over all of the reactants, and all of the products would get multiplied, all of the reactants would get multiplied in the denominator. So you're just multiplying the two K values. If you had to, say, double the first reaction, then K1 would get squared. If you had to reverse the second reaction, then it would be 1 over K2. All right, this reaction's a little bit trickier. We were given 3 reactions and then a target reaction, and we want to figure out the K for that target reaction based upon the 3 given reactions. So in order to do that, in order to get the H by itself, I would need reaction number 2. And I would need to reverse reaction number 2. So I would take reaction number 2 and I would cut it in half. So I would do H goes to H2, and it would be 1/2 H2. So my K for that reaction would be the square root of the reciprocal, because I flipped the reaction, so therefore I have to take the reciprocal of A, and I changed the exponents. I changed the coefficients, so therefore I would have to take it to the 1/2 power, and that would give me H. All right, so in order to get BR, I would take reaction 3, and again, I would reverse it and cut it in half. So it would be BR to BR2, and it would be 1/2 BR2. So my K for that would be, again, the square root of the reciprocal. So since I reversed the reaction, I have to do the reciprocal, and since I halved the reaction, I have to do the 1/2 power, or square root. In order to get HBr, I would need to leave the reaction the way it was written, so I'm not reversing it, so I'm not taking the reciprocal of it, but I would need to cut it in half. It would be 1/2 H2 plus 1/2 Br2 produces HBr, and that would give me HBr. So since I took the coefficients and halved them, I would do K to the 1/2 power, or the square root. And that would give me the reaction. If I want to check that I am getting the correct reaction, I can do that. H plus Br. The half H2s, the half Br2s would cancel, and that would make HBr. In order to find the overall K, I would basically take these 3 Ks and multiply them together. So I could do 7.9 times 10 to the 11th over 4.8 times 10 to the negative 14th times 2.2 times 10 to the negative 15th, and square root of all of that. Since they were each square root or to the half power, then I could just take the square root of the entire expression. Before I put this into my calculator, I found a quick mistake. I had, instead of written negative 41, I had reversed those and done negative 14th. So make sure that we alter that. So that would be to the negative 41 power. That will make a big difference in my answer. Okay, so sorry if that was confusing. So we put that all into our calculator and we get 2.7 times 10 to the 33rd. So hopefully this looks a little familiar because again, this is a lot like Hess's law. So we did stuff very similar to this with delta H previously.